Ladies and gentlemen, this problem is about flow through an annulus. So the annulus consists out of a concentric part through which the flow occurs. So there is the outside, like that. And we have an outer diameter here of 100 millimeters. That, and the inner diameter is 25, and it is insulated on the outside, so there's no heat transfer to the environment. And what we have is water flowing through the annulus like that. Okay. And the water mass flow rate through the annulus is equal to 0.05 kilograms per second, and the inlet temperature is equal to 10 degrees Celsius, and the surface temperature on the outside of this surface, Ts, is 100 degrees Celsius. Okay, so this surface here is 100 degrees Celsius. There's no flow, it's like a solid rod here, and the water can only flow through the annulus, the concentric annulus. And the outlet temperature should be 90 degrees Celsius. Te should be 90 degrees Celsius. And what is required from us is to determine two things. Firstly, the heat transfer rate, and then secondly, the length of the concentric annulus to ensure that the water outlet temperature is 90 degrees Celsius. Now, you have to go and look at the theory that we've discussed on internal forced convection, and you will see that with this type of problem, we have what we call a constant wall problem. So if we look at the flow through the annulus from the inlet to the outlet, the temperature as a function of x, then that is where x is equal to 0, that is the inlet, and that would be the outlet, and that would be equal to L, okay, which we don't know at this stage. So x equals 0 to x equal to L. That is the surface temperature, and the surface temperature is a constant. It is 100 degrees Celsius, so that temperature there will also be 100 degrees Celsius. The water inlet temperature is 10, and the water outlet temperature that is needed is 90 degrees Celsius. So there is Te, outlet temperature, and there is the inlet temperature, Ti. Right, now in the theory we have discussed the fact that with these types of problems, that the outlet temperature can be determined as the surface temperature minus the inlet temperature multiplied by E to the minus NTUs. The NTUs is called the number of transfer units, and that is equal to the heat transfer coefficient multiplied by the surface area through which heat transfer occurs, divided by the mass flow rate and the Cp of the fluid. What is very important with these types of problems where we have a constant wall temperature is that the temperature increase of the fluid will not be linear like in the case of a constant heat flux problem. Therefore, the heat transfer rate, which previously we said can be equal to the heat transfer area multiplied by the surface area multiplied by the surface temperature minus T bulk. Okay, now what is T bulk again? T bulk is the average between the inlet and the outlet temperature. So if we get the average between the inlet temperature and the outlet temperature, then that temperature there is equal to T bulk, TB. Okay. Now, with these types of problems, we cannot use this equation. It is not valid because of the fact that we've got this exponential increase e to the minus NTU increase in the temperature. For these types of problems, we can only calculate the heat transfer rate accurately as equal to the heat transfer coefficient multiplied by the surface area, and we have to make use of the log mean temperature difference, the LMTD. So this is really the essence of a constant surface temperature problem. If we look at this problem also, we shouldn't forget that the heat transfer rate of the fluid, which in this case is equal to water, can also be written as equal to the mass flow rate multiplied by the Cp of the fluid multiplied by the outlet temperature minus the inlet temperature. The mass flow rate has been given to us, and the outlet temperature and the inlet temperature, so we can actually go and get the heat transfer rate very easily if we have the Cp. Now, with any problem, there's no specific procedure or recipe that should be followed to solve the problem. But in general, the things which are important in terms of calculating what is required, which is the heat transfer rate, is in this case, here we can see that we're going to need the Cp. To get the Cp, we need the bulk temperature, and we need to go and get the properties at the bulk temperature. Okay, so we need the bulk temperature, we need the properties, and then to get the length L, we can get it from the surface area. So if we calculate the surface area, then we can get it. Or that surface area there. So we see that we will have to follow it by calculating either the LMTD or calculating the NTUs. To calculate the NTUs, we're going to need the heat transfer coefficient. To get the heat transfer coefficient, we normally get it from the Nusselt number. To get the Nusselt number, we need to know what is the Reynolds number. So those are usually the things which are important in these types of problems that we need to calculate. And when we start calculating it, we will start completing the puzzle in terms of what needs to be calculated. Right, now let's look at the calculation of the bulk temperature and the properties. Here I've shown how we calculate the bulk temperature. It is the average between the inlet temperature and the outlet temperature. So T bulk is equal to the inlet temperature plus the outlet temperature divided by 2. The inlet temperature is 10. The outlet temperature is 90 divided by 2, so it's 100 divided by 2, that is equal to 50 degrees Celsius. Now, for water, we can go and get the properties now at a temperature of 50 degrees Celsius. I did get it from the calculation of using a software program, or you can go and get it from the internet, or you can get it from the textbook that we're using, which is the textbook of Sengel and Gajar. And the properties that I've obtained were firstly the density, which is equal to 988.4 kilograms per cubic meter, the Cp value, which is equal to 4179 joules per kilogram Kelvin, the thermal conductivity K, which is equal to 0.6309 watts per meter Kelvin, the viscosity, which is equal to 0.005472 kilograms per meter second, and then lastly the Prandtl number, which is equal to 3.625. So these are the properties of water taken at the bulk temperature, which is the average between the inlet and outlet temperature. What also helps is in preparation, in many cases, not always, is to calculate the area through which the flow occurs. So that is the area in the concentric annulus, so that is 25 millimeters, okay, and that is equal to 100 millimeters. So the area through which the flow occurs is this area here. So that is the area through which the water flows. Okay, so it is very easy then to calculate the cross-sectional area, which is equal to pi divided by 4 multiplied by the outer diameter square minus the inner diameter square, obviously in millimeters, like that. And if we do the calculation, then it is equal to 0.007363 square meters. The other area which is also important is the area through which the heat transfer occurs. And if we just go look at the sketch again, we see that this is the surface which is at 100 degrees Celsius. There it is insulated, so no heat transfer occurs through that wall. All the heat transfer occurs through that surface there. So if we now go and calculate the surface area through which heat transfer occurs, like that, then it would be that surface there on the outside. Okay, and that would be the length L, and that would be the tube diameter or the inner diameter, which is 25 millimeters. So therefore we can calculate the surface area through which heat transfer occurs as equal to the perimeter P multiplied by L. The perimeter P is equal to pi multiplied by 0.025 multiplied by the length L. We do not have the length L now. It is actually one of the things that we need to calculate. So let's leave it like this. So that is the surface area through which the heat transfer occurs. That is the surface area through which the convective flow flows. The other area which is also very important in this specific case is the hydraulic diameter. The hydraulic diameter, per definition, which we've done in theory and which was also done in the fluid mechanics course, is equal to 4 times the cross-sectional area divided by the wetted perimeter. So that is equal to 4 times the cross-sectional area we've already calculated, is equal to 0.007363, and now divided by the wetted perimeter. And the wetted perimeter consists now out of 2 parts. It is this perimeter here on the inside. Okay, so that is wet. So that would be equal to pi multiplied by the inner diameter, 0.025, plus that perimeter there. Okay, and that perimeter is equal to pi multiplied by 0.1. And if we go and calculate it, the hydraulic diameter is equal to 0.075 meters or 75 millimeters. In fluid mechanics, it has also been derived that the hydraulic diameter is equal to the outer diameter minus the inner diameter, which is equal to 100 millimeters minus 25 millimeters, and you could have also directly calculated from there as 75 millimeters. So now we have some of the most important properties, the areas, etc., and we can actually start with our calculations. Let's start with the heat transfer rate. The heat transfer rate can be calculated. Let's just look at the sketch. Heat transfer rate. The water has been heated from 10 to 90, and it has been given the mass flow rate, and we have the Cp value. So it is very easy to calculate the heat transfer rate of the water directly as the mass flow rate multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. The mass flow rate of the water is equal to 0.05. The Cp value is equal to 4179. And the outlet temperature is 90 minus the inlet temperature, which is equal to 10. So from this we can calculate the heat transfer rate as 16,719 watt, or engineering answer 16.7 kilowatts. So very easily we've calculated the heat transfer rate to the water. To calculate the Reynolds number, we need the velocity. So let's calculate the velocity of the fluid through the annulus from the equation of the mass flow rate is equal to the density multiplied by the cross-sectional area multiplied by the velocity. The mass flow rate is equal to 0.05. The density is equal to 988.4. The cross-sectional area we've already calculated as 0.007363 multiplied by the velocity v, and from this we can calculate the velocity v as equal to 0.00687 meters per second. Right, now that we have the velocity, we can calculate the Reynolds number. The Reynolds number is equal to rho multiplied by the velocity multiplied by the hydraulic diameter divided by the viscosity. The density is equal to 988.4. We've just now calculated the velocity, 0.00687, multiplied by the hydraulic diameter, which is 75 millimeters, divided by the viscosity, which is equal to 0.005472. And if we calculate the Reynolds number, then it is equal to 930.7. Right, now because it is much smaller than 2100 to 2300, we know that the flow should be laminar. So we've got laminar flow. If we have laminar flow, then we know that it takes a while before the flow is fully developed. And we can calculate how long it will take before the flow is hydrodynamically fully developed by using the equation that LH is equal to 0.05 multiplied by the Reynolds number multiplied by the hydraulic diameter. And that is equal to 0.05. The Reynolds number, which is equal to 930.7. The hydraulic diameter, which is equal to 75 millimeters. And that gives us a length of 3.49 meters. How long will it take before the flow is thermally fully developed? That would be equal to 0.05 multiplied by the Reynolds number multiplied by the hydraulic diameter multiplied by the Prandtl number. So if we look at these two equations, then we can see they are exactly the same except for the Prandtl number. So LT, how long it will take before the flow is thermally fully developed, is equal to LH multiplied by the Prandtl number. LH, we've already calculated, is equal to 3.49, and the Prandtl number is equal to 3.625, and that gives us a length of 12.75 meters. Right, so we have done a lot of calculations to prepare ourselves before we now can solve this problem. Now, what is really the problem with internal forced convection? The fundamental problem with internal forced convection is that it is a more complicated version of normal convection heat transfer. We've already done convection heat transfer where you've got a surface which is at a certain temperature TW, the wall temperature. That's that temperature there. And we've got a fluid which has a temperature TF there. And the fluid moves at a certain velocity. And therefore, it is very easy to say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the wall temperature minus the fluid temperature. The problem with flow through internal geometries is that normally the lengths are large and things are not constant. So the fluid temperature changes. So this is something which is not constant. Okay. While the surface obviously is known, What helps in this case is that the wall temperature is constant, but the heat transfer coefficient is not necessarily a constant. So we have things which are changing, and that is what makes internal forced convection a little bit more complicated. So to solve these problems, we need to understand that the heat transfer coefficient depends firstly if the flow is laminar or turbulent. And there are different equations that can be used to determine the heat transfer coefficient. But we first need to know if the flow is laminar or turbulent. What we also need to know is if the wall is a wall where we have a constant heat flux or a constant wall temperature. Now in this case it has been given that it is a constant wall temperature, so that at least that is known. But the other two things which are important is to know if the flow is developed, fully developed, or if it is developing. So all these factors play a role in determining the accurate value of the heat transfer coefficient. So if we look schematically at this problem, again I'm going to plot as a function of x. Okay, there's x. And we have, again, I'm going to plot again that surface temperature there, where we have the inlet temperature of the water and the outlet temperature. And the surface temperature is 100, the inlet temperature is 10, and the outlet temperature is 90. So what we have here, always, the fact that we've got laminar flow means that if this is now the flow through the tube, okay, through the concentric annulus, is that it is going to take a certain distance LH before the flow is hydrodynamically fully developed. There's going to be a velocity profile, so that from that point onwards the velocity profile is going to be a constant. Okay, and then there's also going to be a distance LT, so that is the distance LH, and then there's also going to be a distance LT in terms of how long it is going to take before the flow is thermally fully developed. So from this point onwards, if we measure the temperature difference, then the temperature difference between the fluid and the wall is going to be a constant. Now, this is the length L. Okay. Now, we've calculated that this distance is about a little bit more than 3 meters. If we just look again here, 3.49 meters or 3.5, and then LT is about almost 13 meters. So again, if we now look at the sketch, we're going to have the situation where the heat transfer coefficient is only going to be a constant from this point onwards. So the heat transfer coefficient is going to do something like that. And that is a very, very important thing to remember. Okay. So while the flow develops, when it starts, the thermal boundary layer is going to be at its thinnest, and therefore the heat transfer coefficient is going to be at its highest. But then the heat transfer coefficient after a while is going to become a constant. So there it is going to be a constant, and in this part it is going to be a function of x, so it is not a constant. So in general, this problem, there we can say the flow is fully developed, and there the flow is developing. Okay. Now what have we determined from our calculations? We've determined from our calculations that the flow is laminar, and therefore we've calculated these distances, but we do not know what this total length is. So if the total length is going to be smaller than about 13 meters, 12 to 13 meters, it means that most of the flow is going to be developing. However, if the total length is maybe going to be 1,000 meters, then this distance in comparison with the total length is going to be small. So just to start, we have to make an assumption. And the assumption that we're going to make is that the flow is fully developed. So it's fully developed. The heat transfer coefficient is a constant, and that the heat transfer coefficient is a constant right through. So therefore, we are making the assumption that the heat transfer coefficient is a constant right through the tube. It might not be correct, but that is something that we're going to start with. Now, where do we get the heat transfer coefficient? Well, you might be tempted to say, well, we've calculated the hydraulic diameter, so it is very easy. We just say that is a tube, and that is the hydraulic diameter, and it has been given, we have determined the flow is laminar, okay, and we've got a constant wall temperature, and therefore, we are making the assumption the flow is fully developed, so therefore the Nusselt number we have derived it should be equal to 3.66. However, you have to be very, very careful. In the textbook and also in the literature, the Nusselt number for these types of configurations, laminar flow with a constant wall temperature for fully developed flow, has been determined for different geometries. Like for a circular tube, for a square, for a triangle, but also for flow through an annulus, like that. Where do we get the results for flow through an annulus? It's in the literature. You can go and look in the textbook of Keyes and Perkins of 1972. Or in our case, you can go and look in table 8.4 in the textbook of Sengel and Gejar. And in table 8.4 in the textbook of Sengel and Gejar, you will get that the heat transfer coefficient, which is been given for different ratios of inner diameter divided by outer diameter, is given for different Nusselt numbers on the inside and different Nusselt numbers on the outside. So, for example, if this ratio is equal to 0.05, then the Nusselt number on the inside is equal to 17.46, and the Nusselt number on the outer wall is equal to 4.06. I'm not going to write down all the values, but the important one for our case is equal to the ratio of 0.25. Where do I get this ratio from? I get it from the inner diameter, which is 25 millimeters, 0.025, divided by the outer diameter, which is 0.1. So this ratio is equal to 0.25. And then the Nusselt number on the inside is equal to 7.37, and on the outside is 4.23. Now, many students find it difficult to understand what are the differences between these two Nusselt numbers. Well, the answer is in the fine print. And the fine print, if you go and read it very carefully, will tell you that these results are valid for cases where, firstly, if you've got an annulus and the heating is on this wall, while on the other wall we have an isothermal wall. What does isothermal mean? It means it is a constant temperature. So then it would be Nusselt on the inside. While if we have the case where this is an isothermal wall and the heating occurs or cooling occurs on that wall, okay, then that would be Nusselt outside. So in our case, if we look at this, then we will see that the Nusselt number is equal to 7.37. So take note, it is much higher than that through a circular tube with an hydraulic diameter. We wouldn't have, if we did the calculation using that, then we would have made quite a significant error. So now we've got the Nusselt number. So the Nusselt number is equal to 7.37. The Nusselt number is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by the thermal conductivity K. The Nusselt number is equal to 7.37. It's equal to the heat transfer coefficient multiplied by the hydraulic diameter, which is 0.075, divided by the thermal conductivity K, which is equal to 0.6309, and with that we can calculate the heat transfer coefficient as 61.99 watts per square meter degrees Celsius. So now we have the heat transfer coefficient. If If we just go back to these equations here, we can see that from this equation, the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. That we can calculate the required surface area if we first have the LMTD. Right, the LMTD, it is very, very easy to calculate the LMTD. Let's look at the sketch. The LMTD is always, let's go to the sketch, this temperature minus that temperature. So it is 100 minus 10. Let's write it down, 100 minus 10. Okay, minus, look at the sketch, that temperature minus that temperature, 100 minus 90. Okay, 100 minus 90, and then divided by the ln of those two exact terms, 100 minus 10 and 100 minus 90. So we can calculate the log mean temperature difference as 36.41 degrees Celsius. Right, now that we've got that, we can calculate the surface area from the equation. The heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. The heat transfer rate is 16,719. Is equal to the heat transfer coefficient, which is equal to 61.99. The surface area through which the heat transfer occurs, we've already calculated it as pi multiplied by 0.025, that is the perimeter, multiplied by L, multiplied by 36.41, and the only unknown is the length L, and the length L is 94.3 meters. Right, now we've calculated everything that has been asked from us. However, that is not the only way how we can calculate the length. We could have also made use of, let me just go back to this equation, by using this equation to first calculate the NTUs. And once we've got the NTUs, we can get the surface area or the length from this equation. So let's do that and see if we get the same result. So the outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus NTUs. The outlet temperature is 90 minus the surface temperature is 100 minus the surface temperature 100 minus the inlet temperature, which is 10, e to the minus NTU. And the NTUs can then be calculated as 2.197. It is always good that, when you calculate something, that you think about it. We have done it in the theory that typically when this value is approximately equal to 5, then this temperature and that temperature will be the same. So the fact that we are calculating something which is less than 5 is good. It should be like that. Okay, so if you've calculated an NTU of 21.97, you must immediately know that you've made a mistake and you need to go and check it. So now that we've got the NTUs, we can say that the NTUs is equal to the heat transfer coefficient multiplied by the surface area through which the heat transfer occurs, divided by the mass flow rate and the CP value. The NTUs is equal to 2.197, is equal to the heat transfer coefficient, which is 61.99, multiplied by the surface area through which the heat transfer occurs. That is equal to pi multiplied by the diameter multiplied by L. We've already calculated that, divided by the mass flow rate, which is equal to 0.05, divided by the CP value, which is equal to 4179, and from this we can calculate the length as 94.3 meters. So we're getting the same length. Right, now let's just evaluate the assumption that we've made. So what we've calculated now is that this length is equal to 94.3 meters. Okay. if the flow would be fully developed. And LT, that distance there, how long it will take before it is thermally fully developed, is equal to 12.65 meters. Okay, there it is. And this in total represents 13%, only 13% of the total length. So 80% of the flow would be fully developed. So in this case, we can say that it was a good assumption that we've made, just coming back to this, that the heat transfer coefficient is a constant. If it was the case that this total length is less than 12.65, then it would have been necessary to calculate the average heat transfer rate for the developing flow. It would have been more complicated, but there are equations available that can be used to calculate it with. And then the last thing that we need to do is just coming back to the fact that normally we calculate the bulk temperature between the inlet and the outlet temperature. Now we've done it in the theory that for constant wall temperature that is not accurate. Typically we get something like that. Okay, but that is where we've started. Now we've determined this LMTD, which is a very good average of the temperature difference. So what we can do if we want to is to go and calculate a new bulk temperature by saying that the new bulk temperature would be equal to the surface temperature minus the LMTD. Okay, the surface temperature is 100 minus 36.41, and that would be a new bulk temperature of 63.59 degrees Celsius. Now, at that temperature, we can go and get all the new properties. Okay, and what properties are we talking of? We are talking of the density, we are talking of the Cp value, the K value, the viscosity, and the Prandtl number, all of them. We can go and get it, not at 50 degrees Celsius, but rather at 63.59. That would be a better average than the bulk temperature. And then we can recalculate everything. And if you do that, then you're going to calculate that the length is 92.34 meters. If we compare it to that length, then we can see that it is within a few percent. So I think it was a good assumption, but if you want to do a refinement, then you can do it like that. Ladies and gentlemen, thank you very much. That is the end of this problem.